So, welcome everybody. Today's presentation will be given by Álvaro here. So, Álvaro studied physics and electronic engineering in Spain, and now he's studying applied physics here in Delft. His main interests are related to quantum hardware, solid-state physics, and so quantum technology in general. And as you may know, he's also very interested in spins. So he has already talked once about spin, and he's going to talk again about spins today in some sense. So the paper he's going to present today was published in 2019, and it's a paper about high coherence spin states in carbon nanotube-based quantum dots, which are driven with cavity photons. It was written by many authors, but among them we can list here three names. They all work in the physics laboratory of University of Paris, in Sorbonne University, and one of them, Mathieu Degenerate, is also the CEO of a very nice startup in Paris, who is the only startup working with the qubits in carbon nanotube, which is C12. And actually, Álvaro will also take part in an internship from this summer in this company. And the other institute that collaborate to this paper are lots of universities in Paris, Sorbonne University, the Centre National for Research Scientifique, the Mines Paris Tech, and also Charles University of Technology. But yes, I will not steal any other time from our presenter, and so I leave the word to Álvaro here.
Thank you so much, Mateo. Okay, so the paper we're going to be talking about today is highly coherent spin states in carbon nanotubes coupled to cavity photons. So as with Hjalmar last week, we have like a very long name. We don't really understand what many of these words mean together. So we will try to get the concept clear. Okay, so it might not feel like it, but we're going to be talking about qubits in this presentation, and in particular about how we prepare the hardware to make qubits in real life, right? So we are going to be going to the specific materials and techniques that we need to be able to work with qubits. So for that, you all know what a qubit is, but we are going to be mainly talking about how to really implement a two-level system. Because in real life, in this universe, there are no two-level systems. We have many level systems. And we have to go to a subsystem that is only two levels. Then we need to be able to interact with that two-level system. So we need to be able to drive our qubit, to read the state of the qubit, so we need to be connected to it. And lastly, there's another important point of qubits, which is noise. How is this two-level system going to be affected by its environment? As you may know, there are many flavors of qubits. Here we can see some examples: superconducting, NV centers. But today we are going to be talking about a very big part of qubits, which are called spin qubits. Okay, so it's quite simple. When we start thinking about two-level systems, the first thing that comes to our mind is, oh, okay, I have a 1/2 spin. I'm going to put a magnetic field, very big, and voila, I have my Siemens splitting, and I have a two-level system, right? Okay, so let's do that. But we need to put our electron. This is going to be our spin 1/2 particle, and we're going to have it somewhere to be able to work with it. So we need to confine an electron. And how do we do that? With a quantum dot. So the first thing we're going to do is talk a bit about quantum dots, what they are, how we build them, and a bit of their characteristics. So okay, a quantum dot is just a zero-dimensional system where we can have a fixed number of electrons, and that is very easy to work with it because we can just tune some parameters and work with them just by varying some voltages. So very easy to work with them. What we have is, here we can see a source, which is just a normal metal, then a drain, also metal, and we see two tunnel barriers, which is what isolates our system from the outside. So inside here we can have isolated electrons, and here we can see that we have some levels where we can start adding electrons. Then we have a gate voltage with which we can push up or down these levels. And with this, we can go to different states of this quantum dot. In this first image, we can see how in between the bias window, which is this part in between the mu d and mu s, we have no levels. This means that no electron can jump inside the quantum dot at leaf. So here we measure nothing. However, here we have a level that sits right in between these two levels. So an electron is able to jump in, tunnel through the barrier, and then tunnel out, so we are able to measure a current. Okay, now we know a little bit of what a quantum dot is. Let's see what the easiest qubit can be made with this quantum dot. So let's focus on only a single electron level in our quantum dot, which is spin degenerate, right? I can have here in the same energy level, spin up or spin down. I turn on a magnetic field. It's usually quite big, that's what I need, to get out of the thermal noise. And I get a Twolevel system. I have spin down here and spin up here. So this can be my Twolevel system. Now, how do I operate it, with it? How do I initialize states? How do I drive them? That's something we're going to try to see here. So we start with an empty dot. We have, with our gate voltage, remember that we can tune the height at which our levels are. So if I push them up, if an electron is here, it will just tunnel outside and relax. So this is empty. This is how we start. Then I can do the opposite and push the levels down. And then an electron can hop in, either in this state or in this. If it starts here, okay, I have my zero, it's fine. But what if an electron comes inside here? Then I have to wait some time, several times the relaxation time, until the electron goes down here. So then I'm sure that I am in the ground state. Okay? Now, once I know that I have the ground state, I can work with it, drive it. We will talk about that later. But then I need to read it. I need to know at the end of my operations in what state my electron is. What I can do is push up, but not as much as here, just so that the two levels are in between the Fermi energy of the source. In this way, if an electron is in the excited state, it will jump off and I will be able to measure a current. But if it's here, it will be trapped. It cannot turn out. And we can see it here. This is like an experimental, well, this is like a model of an experimental measurement. And we see how here, if my qubit would be in the state 1, I would see here a current, like these poles. But if it's not, I would measure nothing, because the electron would just stay inside the quantum dot. I can do this 1,000 times, do my statistics, and know the state of my qubit. Okay, this is very nice, but now I have to implement this in real life. So we need to choose from all these materials that we have, how do we make a quantum dot? The preferred elements are these here, because the group 14 has 0 nuclear spin, and that helps a lot because a very big source of decoherence is nuclear noise. When you have nuclei next to your qubit that can make interactions with your qubit, that can distort your measurements. These have zero nuclear spin, so you don't have that in principle. But so far, there has been a lot of work done with silicium, germanium, gallium arsenide, and they work a lot with that, but there hasn't been a lot of work done with carbon yet. So that's what this paper is about, how to implement a qubit through quantum dots in a carbon nanotube. So yeah, until here, it's kind of an introduction to see a bit how this works. We saw the simplest example of a qubit. Now let's see what they do in the paper, which is quite more complex. So the first thing I'm going to show you is the hardware, how it looks like. So this is the circuit. You have some DC pads. This is just to change the voltages we have been talking about. Then you have some rate of frequency, which will have something to do with the cavity that they mention in the title. If we zoom in here, we can see this, which looks pretty weird. The only thing we can see is that it's very small. This is like 10 times smaller than a hair, pretty small. Then we zoom in more to this region, boom, and we see our carbon nanotube, which is this very, very small thing here. You can see a scale, 0.2 micrometers, or even much smaller than this. And let's understand a bit what we have here. So we have our carbon nanotube. This is where our quantum dots will sit, but we will not have one, we will have two. So if we have two quantum dots, we will have two gate voltages, which are left and right, for left quantum dot, right quantum dot. And then we have other voltages that what they will do is prepare an electrostatic landscape so that we have our electrons confined, right? If I put a high voltage here, and high voltage here, and a low voltage here, electrons can be in the middle, but they cannot go out. So that's how we prepare our quantum dot, because we can only have if we have a nanotube, so they are already confined in one dimension, and we confine them further with these potentials. As well, we have here some ferromagnetic material that will set the quantization axis of our spins inside the quantum dot. So they will make a splitting of the energy levels, and we will have a preferred direction for the spin. Okay, so this looks quite more difficult than what I explained before, because now we have like 4 levels that look like this. And one important parameter that I want you to see here is that depending on what gate voltages we set in the left or right quantum dot, we will have that these two levels are closer to these or more separate. This will be quite important later on. And we see here the energies, and this is where we will be working. This will be our 2-level system. Okay, so now we have 2 quantum dots. This is quite different from what we had before. Now we can have a qubit in 2 very different ways, because we can say, okay, 2 levels, electron in the left or electron in the right. That's 2 levels, right? So I can have it here or I can have it here. You can forget about these 2. That would give us a qubit, right? So that's okay. These are called charge states. What's wrong about this? That any small variation of our voltages will affect the state. And it's very difficult to have no noise in voltages and charges. This is like you have a circuit and you will have radio frequency waves flowing through electrons that can flow around, so that changes the electrostatic landscape next to your qubit. So this qubit is very, very bad. Like it will have a super high decoherence rate. So what we can do is, the detuning we talk about here is very low detuning. If we go to a very high detuning, our electron for sure will be in one of the 2 sides. Okay? So we have that the wave function is going to be like, it's going to be in one of the 2 quantum dots, either left or right. And then our qubit will have to do with the spin. And this breaking of the degeneracy is given by the magnetization of this material here. And here we almost have no interaction with this charge noise that we talked about before. So these spin states are much more resistant to noise in the voltages and charges around. So this is what they will use to make their qubit. Now with this, how do we drive it? So the main interaction that will happen here, in order to be able to change the state of our qubit, will have to do with these charge states. But wait, like we said, this is bad, right? The thing is that if we go to a complete spin state, like it's 100% spin state, I cannot talk to my qubit. Because, well, I could do it, but with high magnetic fields and whatsoever, which is kind of difficult. But if I have mostly spin state, but a little bit of charge state, so I'm somewhere in the middle, I can do it with electric fields, because charge states know about electric fields. So if I go to a spin state, and I throw a microwave, I can somehow drive this qubit and change its state. It's a bit weird idea, but this is how it works. So we have like 3 different things that will change the state of a qubit, as we saw in quantum hardware, the ones that you do it. This has something to do with NMR, so like you have a magnetic field that oscillates in time, and with that you can change the state of your qubit. And we have 3 different sources of magnetic field. One is just an external magnetic field that you can turn on. Then you have the AC, effective magnetic field, which is an electric field that interacts with the charge part of your qubit, which is translated to the spin part, and that gives you an effective AC magnetic field. And then another is a DC magnetic field that has to do with the tuning. So somehow with this interaction with a hybrid spins charge state, we can drive our qubit. Now, what are the results of this paper? What they want to prove is that you can do a qubit in this carbon nanotube. So the main things that they need to know is, okay, does the quantum information remain long enough so that I can perform operations? So that is given by the decoherence rate. And we also need to know if I can act on the qubit strongly enough. Can I perform operations on it? So can I interact with it? And that's given by a coupling strength, which is the coupling strength between the spin state and our cavity. So the electric fields that we are generating. Some results that they show is that, for example, for spin states, we have that the coupling strength over the decoherence rate is larger than 8. But for example, for charge states, it's like 0.015. And this gives us the idea that charge states have much higher decoherence rates than spin states. And well, these are some numbers that don't really give us anything, but the decoherence rate is given by like 250 kilohertz, more or less. I don't know if you know any numbers of other spins. I don't, but okay, and what they measure is this, okay? So they do a measure for different detunings. So they try to go to different hybrid states in between charge and spin states, and they see how the system behaves. So we see how when we have high detuning, we are in a spin state. So this has a low decoherence rate, but it's also more difficult to interact with the qubit. And the other way around. If I have a lower detuning, I am more close to a charge state, so I have higher decoherence rate, but I can also interact more. And then they define a unitless quantity, which is given by the coupling strength squared, also the decoherence rate, and the kappa. The kappa is something that tells you about the quality of the cavity, so how many photons does the cavity lose, something like this. And they find with this like the sweet spot where with this decoupling, with this detuning, you will be able to use your qubit in the best performance. And what are the conclusions of this paper? So they prove that you can drive a qubit in carbon nanotube by using microwaves, which is perfect. Okay. Now there's something that we need to do quantum computing apart from this, right? We need 2 qubit gates. How do spins in different quantum dots talk to each other? Because in this paper they promised us that this technology will be super good to scale quantum computers, to have loads of qubits in the same cavity. But for that, we need to be able to perform 2 qubit gates. And they state, yeah, you can do this through virtual photons that go from one qubit to another through the cavity, and then, yeah, they can talk to each other. But they also say that this remains to be proven. So this remains to be proven. We don't know if you can do it. It sounds very fancy because they say that you can put as many carbon nanotubes in the same cavity as you want, and they can all interact with each other. So you have all-to-all connectivity, which sounds amazing. You cannot do this in a superconducting platform, but they haven't done it yet, so we will see. But okay, apart from this, they have gone 100% times better than the last work on carbon nanotubes, 2 to 4 times better than the last one done in silicon, 40 times better than the one done in gallium arsenide. So this sounds good, right? And they also say that they can do better because we said that carbon doesn't have nuclear spin, but that's not entirely true because it's only carbon 12, the one that doesn't have. Carbon 13 does. So you need to purify your carbon so that it has as less concentration of carbon 13 as possible so that you don't have that noise. And then your decoherence rate would be lower. And this is an image of how qubits are interconnected in a superconducting platform. So you can see here that you are quite limited by the amount of microwave buses that you can connect to each qubit. So you have like a spatial constraint of how many buses you can attach to each one. So this makes it hard to scale these kind of systems. So if it is true that they can do it, as they say here, by just communicating through a very big microwave cavity, that would be super good. And that's it. Thank you very much.